so let me give a brief background. When I was invited for, or the discussions were going on for this topic, especially on the speech technology. So I told them that I'm not from the core background of speech communication, but what I can tell you is something, some interesting applications that we build using speech recognition algorithms on remote robot control, and that is what I'm going to present today. So the intention is that once if this kind of applications interest you, maybe this can open up new research challenges for those who are deep into the core subject of speech recognition and speech technology. So I just wanted to set the context right and the expectations right. I'm sharing my screen, and this will not be a very long talk. I mean, this will be more on a system talk. Let me just try. Okay, I need to add audio. Yes, sure. Right. Please confirm if you can see my screen.
Yes, kindly zoom it. It's visible.
Yeah, I'll zoom that. So, all right. So this is basically speech-based maneuvering of remote multi-user telepresence robot with implicit source separation and in radio coverage prediction. Now, this radio coverage prediction, I'll not go into the detail because that itself is a huge topic, and I'll just put the reference of our publications. So, without much delay, let me get straight into the problem. So, we are basically working back in during the time frame of 2019 to um, about 2023. We were actually working on developing from scratch a telepresence robotic system with embodied intelligence. One of the intelligent operations of that we perceived for that robot. So the idea was to facilitate the remote operator as much as possible, so that more and more intelligence can be put on the robot while the human operator still has the control and the supervision remotely. But the robot can facilitate by understanding the context of the remote scene, understanding the context of the operator as well. So this problems is basically in falls in the class of understanding the context of the operator, right? So we try to make the robot as human as possible. So what we wanted to do is that while there is this normal audio video conferencing is going on through the robot, I'll come to what is the definition of telepresence and what are the complexities that I'll come to later, and what is multi-user telepresence. That is a unique concept, a patented concept that we have. But before that, just let me give you the brief of the problem. So the robot and the human operator I mean, the human operator side console and the robot terminal are just, you can consider as two machines, whereby audio video conferencing can happen, and at the same time one user can control the robot or maneuver the robot. So for the audio video conferencing part, it is same as or similar as what we are doing right now over Teams. So we build our own solution called teledrive. uh, Now the question is that in this case, the human operator has to, while the normal conversation is going on, the human operator can instruct the robot to do something without sending explicit control using either joysticks or some or some control buttons on the console just by voice, right? So that was the idea. Um, so here you can see that there is a situation depicted here. So there's a meeting going on. There is a robot at the at one premise, and there is a human operator at the another part of the world, and the robot needs to go close to the board to see what is being written there. And so the human operator, without touching any console or anything, it is just saying that it calls the robot by name and tells that go to the board. And this unique keyword was given by us, Avixa. It rhymes with Alexa, but uh, Avixa has something with, I mean, in Sanskrit, it has something to do with vision also. So, because the remote operator actually sees through the robot, so the keyword was chosen as Avixa. And when the robot tells Avixa to go to the board, the robot understands that there is a command and it goes to the board or whatever is the instruction there. So, mostly these were for navigation purposes. Now we need to understand the complexity. So we have experiences with Alexa and Siri and all. Now the complexity in these cases is that these kind of devices, they are dedicated for this kind of work, and the speech engine basically listens, is always in a listening mode, and there is no other interaction. I mean, there is no audio video going on, right? So it is, I mean, normal video chat or nothing is going on. It is just, it listens, it takes the command and executes. And also, in this case, the entire speech processing is happening. I mean, the interaction is very much local, right? So it is just in your personal premise. But in this case, it is not. I mean, it is across the, it can be across the globe, thousands of kilometers away, and the effect would be similar. Only thing is that it is just like a servant. So the I mean, or you can say like in Kurukshetra war, there is Sanjay who is actually narrating the war, but at the same time, maybe through Sanjay, many people are speaking. But at the same time, if Dhritarashtra has some problem and tells Sanjay to bring, suppose a cup or something, and Sanjay understands that this is not related to the live telecast, but it is related to something very personal to Dhritarashtra. It is something similar you can think about. Only thing is that in this case, the person is much, I mean, far remote. So, lot of engineering challenges are there. Now, coming to telepresence, what really is a telepresence robot? So, as you can see, a telepresence robot is nothing but a robot, a audiovisual unit, um, uh, sitting on top of a wheel. So, and there is a remote person who can control the wheel with real-time connectivity over the internet. So, this is not really limited to a local premise, and there will be a person. So the person can meet and greet people at the other end, and will feel like, as if he or she is roaming through that robot in the remote premises, right? So this is one of the way how we can bridge the gap, and we can make the person feel virtually in a remote space. Okay, right. So now we had a patented concept. We have this patent in both Europe and US as well as India. So we devised something called multi-user telepresence, and there are some unique network architecture that we had put. Why? So by multi-user telepresence, what we mean is that so today's most of the telepresence solutions that we get in the market, they are all tied for one-to-one communication. So there will be only one operator joining remotely, and there will be the robot. There will be only one robot, so the interaction is one to one. But in multi-user telepresence, there can be multiple users joining the session, multiple human joining the session, and one human can just request for an upgrade as an operator. As you can see here, the user one is the operator who is controlling the robot, and that is why he has got the control interfaces, while user 2 is just the observer. So they they all can see it, right, uh, here. In this case, if the user 1 can operate this robot, and user 2 can actually only watch what is happening. uh, and if the user one is done with his or her actions, then the user one can leave it and just relinquish the operator role. The observer can take it up. Now, this makes the voice command control far more difficult, because as we see in normal control operation, there is only so only the operator is allowed to send the control or the commands to the robot. The observer is not. But the question is, when it is a matter of speech, so audio video is flowing, right? Because this guy is also able to speak, this guy is also able to speak, and the robot listens from both. The question is that the robot, so what goes to the audio video pipe that goes to the robot is is a single pipe, and the robot has to understand that whether the command is coming actually from the operator, because the observer should not be able to talk. And also at the same time, while the operator is talking, the observer may is should be allowed to talk, I mean, freely. So the problem is that the operator has to talk, has to utter the command, while the observer may continue the normal audio video communication. And we cannot tell the observer to shut down his voice or keep silence, because the other operator, remote operator, is delivering a a command, because that kind of application will not really be acceptable. So that is another challenge. So these are the design questions. So one is that during the conversation, how does the robot know that the voice from the operator contains a command for it? So that is, we solve it using wake word, which is very conventional, and also a timeout to identify when the command finishes, and whether the command is at all coming, or the person is just using the wake word and then going silent. So we need to preserve the resources accordingly, so that we do not fall in the endless loop of listening for the command. And in a multi-user scenario, when multiple people are talking, how does the robot understand whether the command is from the operator? How do how to separate the sources, right? So the way we did this, so this is the overall architecture. Now, so there are, as you can see, there are two cloud instances, and there is one edge instance. So the edge is basically allow the robot to offload its computation, its intelligence, and that offloading is also for ASR, as the speech recognition and all, right? and also it has to detect the local environment. So we do the speech recognition module. So there is one speech, we keep the speech recognition module at the operator plane, at the human user plane. So what happens is, whenever a user takes control as an operator, the ASR module is actually connected to that operator. So the topology completely changes, right? So it's a kind of switching connection that happens between the ASR module and the operator. So for at a time instance T1, if there's one operator here, if this guy is the operator, ASR module connects to this. In time instance T2, if this guy is the operator, then the ASR module connects to this guy, right? So that way, there is an implicit source separation, not just going to the signal processing or level, or not going to any putting any complex AI over there. This is just by using the network topology intelligently and flexibly. We can do the source separation there. It is a separate question that if there is too much of noise at the operator side, then how do you identify the voice? So that's a typical problem that we all face, even with the speech modules that are provided with the keyboards, with the speech-based keyboards, and even the Google assistants and all. So that crosstalk, local crosstalk, is definitely a problem, and that is something people can work on. I don't know the exact state of the work on that, but so far as the remote crosstalk is concerned, if we had taken this ASR module for command detection here, then the problem is that all the speech is coming through one pipe, all the media is coming through one pipe, and and the source separation becomes very non-trivial. So this ASR module identifies the command, and that command is provided over a dynamically established direct link between the or P2P link between the human user and the robot, and the robot then gets all the navigation commands and image grounding and everything there. So the idea is that the ASR is, we are not doing the ASR at the robot side, but we are keeping it at the cloud, and this is happening, dynamically based on the human and the, I mean, which human is actually is now the operator. Now there can be some more intelligent operation can be done if you really have resources. Then based on the location of the operator, this ASR module can be placed intelligently. So you can just switch the location of the, that is why this cloud is separated. So if this operator is currently situated in India, then maybe the ASR module can be offloaded to an Indian server. Now if this person who is an observer becomes an operator, this person can take up the same role, and the ASR module, maybe he's speaking from Europe, then the ASR module can be offloaded to an instance in Europe. So that kind of that kind of flexibility can be deployed if resources are available. So what we do is, so there are two stages. One part is wake detection, and the other part is command detection. So wake detection. Now what we deployed over there is that the ASR module actually works we provided a duty cycle to the ASR module. So every time it just wakes up, it just says that it just wakes up for a while just to listen and sleeps. And so and that thing is also synchronized at the operator side, because there's a voice recorder that works there. I mean, so that also just keeps on telling that if you have to provide me a command, then please provide me. This is a I'm awake now. I'm listening. It's like that. So it's a time division kind of approach we took, because that was the simpler one, given the tight deadline within which we had to deploy this, because we had to deploy this entire thing based on our telepresence software, what was existing. We had to put this feature in about 3 months or 2.5 months time. So that is the approach we took, and that makes life a little bit simpler, because we can define a state machine based on which we can guide the operator to just to wait for the appropriate time and deliver the wake word, so that that syncs with the ASR module, and that saves our resources also. Because one thing we have to understand, that we are making it as democratized as possible. So we are not putting the ASR module in the local terminal, because that will have two implications, bad implications. One is that this ASR module needs to be downloaded right on the device of the end user, and secondly, this will keep on consuming battery for the user. So because you not only just record, even if you are offloading, then you will continuously transmitting the signal. That's a privacy issue as well, because you will be constantly transmitting the recorded audio, whatever audio video is going on. You will be constantly transmitting that. And on a continuous stream, segmenting the stream, and there is I mean, on a continuous stream, if the user is not aware where the wake word detection module is working, so what will happen is that there can be fragmentation of the speech, and that becomes a bit difficult for to stitch the modules and understand whether certain syllables have gone in a different fragmentation, and certain syllables are in another fragmentation. So that is why we defined a very um, clear state machine. And then the command detection was also done in the same ASR module, but with a different dictionary, and that worked also on a timeout basis. So after the wake word is successful, a certain timeout period, the ASR module will listen to the command, and that is normal in any of the modern speech based assistants, right? So the question is where the compute happens. So the compute happens here. This can be put to a localized compute, as I said, and the source separation happens this way, right? Without making things much complicated. So this is the state machine of the operator side, and you need not go to the details. I have given the paper that was published as a demo in ComsNets. I've given this in the slide later. So as you can see that, so it will be snoring, and time to time it will wake up, and then there will be the command listening. It will listen to the command. Once it listens to the command, then it will, so it once it gets the wake me up is successful. So it will actually go to command validation, and then it will go to command transmission, right? And this is the on the ASR side. So once the wake, so this was actually on the operator side. So the operator side, there has to be some mechanism to send the recorded voice from, I mean, to a separate channel, because there is one audio video channel which is going, one audio video which is between the robot and the between the human operator and the robot. But In this case, there is another audio channel that was open to the ASR module. So when to put through this audio channel, that is what was decided using this state machine. And this is the state machine at the ASR side, because ASR side, as I said, will keep on working on the duty cycle. So once a command is recognized, it is found that there is a sensible thing, so it will validate, and then it will again go to snoring. But once the command is validated, this command will get to the operator. And okay, so this is the command transmission. So what will happen is that once the ASR module detects, so the ASR module does not have any connection with the robot. Once the ASR module detects that there is a command, and it will send that response to the human user, and this will flow the detected text will actually go to the robot, where the text will be analyzed and the navigation command will be processed. Okay. And so, and if it finds like there is something related to the scene current environment, so it will then go to the image grounding module, and the navigation will happen accordingly. So the image grounding module is basically identifying the object of interest for the operator. So if I say that go to the person standing near the door, so it will identify the door and the person, and then the navigation module will guide the robot towards the door. So identifying the door and identifying the location that it needs to go on, the geographic location it needs to go, it will be done by the image grounding module. So for implementation, we did not go to much sophisticated thing, because one of our teams, they tried with web to web for a more generalized concept, but we found that, I mean, many glitches were coming. We are not sure that whether that was a problem with the training of the web to web, um, but we needed to do it in a very confined cases. So we used very old phonetics based system, so it is not very AI savvy stuff. So we created two dictionaries. One is the different possible utterances of the keyword, and we broke that into the phonemes that were given by pocket swings. This is I think Carnegie Mellon's solution. And there was another dictionary, so that was used for the command detection phase. So the earlier one was for wake word detection phase, and the next one is for command detection phase. And in the command detection phase, we limited the possibilities of the commands, because we were working for a office environment, like there will be laptop, there will be door, there will be bottles, there will be chairs, there will be printers, so like that. So we made a very a large list of the possibilities. Of course, that is not how we want this to happen. We want to make this generic, and that is where the our the people working on speech detection science and the AI modules have a lot of things to work, a lot of advancements to be done. And also uh, we wanted this thing to have zero training. So that is why the phoneme actually worked very well, because what we found is that even people with different regional biases in their I mean the vernacular effects, Indian from different region of India, they have the vernacular effects on their English pronunciation. So that was fairly well covered when we broke that into suitable phonemes. Like uh, we had the biggest problem with door, because door and board. was most of the time they are confusing, because they put the door and board as per the American accent, the American phoneme. So we had to make, I mean, we had to put an extra emphasis on the R, and extra emphasis on the D, in the phoneme structure. So that way we kind of resolved this thing. We won't say that it worked perfectly well. There is a problem in terms of we needed to clip the signal. So if you speak very close to the mic, pocket springs does not work that well, because the noise that it generates because of higher amplitude of the voice, uh, that destroys the phoneme structure. That creates an additional noise. We didn't put any low pass or any filtering over there in the software. So, but if you speak like the distance that I'm speaking right now with my laptop, it worked fairly well. And the entire thing was, the entire state machine and everything was built on JavaScript, and this was published in ComsNets, as a demo in 2024 edition. So let me see if I can play this video. So there's a demo video. Let me see if I can. Oh, why it can't play? Uh, just a minute. Let me try from somewhere else. Um, for some reason, the video has stopped working. Give me some time. I'll get the demo working. Um, oh, it doesn't play. Okay, I got it. Uh, Unfortunately, I'm not able to find the video. I'll try to get it, but this is not allowing for some reason. Maybe because of the uh, of the conferencing account that I'm working on. Probably for that the video play is prohibited. There are certain policies, but otherwise it should run. Actually, I tried before joining this meeting. So let me just give you uh, some screenshots actually from the paper. Let me see. Right. Uh, so this is the paper actually that we published. Let me give you some screenshots from there so that I can get it. You can understand. Yeah. So it was basically there's one operator who joined from Bangalore, and there's from one office there's one person who is the observer, and the robot was in Calcutta in our lab, and this person for every for every speech cycle. Okay, let me open the word document. Yeah. So there is the it's not very clear, but this is where it says that wake me up, and this person talks about calls the robot by the name Avixa, and then it just wakes up, and then the person tells that go to the TV. So when the robot detects that there's a go to the TV, so it just says whether you need to confirm by yes or no whether this is the correct command, and the person says yes. So once the person says yes, so the TV gets detected, okay, because that is where the image grounding happens, and then it says that I'm executing, and it starts to move and goes to the goes near the table. And as you can see, there's this half round um, uh, indicators, and these indicators change their colors as the robot move. So this is basically the while the robot is on move, it also detects the possible radio outage probabilities in in 4 or 5 different directions. So these color codes are actually indicating that which direction has higher or radio outage probability, because then the robot will lose connection. For some reason, I'm not able to play the video, but that is it. And um, so uh, for any further information, you can actually on this radio part. So we had a paper published in the same 2024 in the ComsNet's main track, sensing best connected future path for mobile telerobot. So we actually integrated these two components, the speech and these two, and although the solution has a combined impact, but we we published it in two different tracks. So the speech-based command was in the demo track here, and the radio sensing part was in this part, so you can actually go through that. So with this, I'll conclude the talk. I'm sorry that I could not play the video. That would have been really interesting. But let me just keep on trying we uh, while we uh, conclude it, right? Um, so if you have any questions, we can take that questions.
Yeah, dear audience, if you have any questions, please go ahead.